Welcome to the Backup Podcast, a show on how technology is changing the way we live and do business. I'm your host, Ioannis Bakagiannis. Backup is ready to start. Hello. This is episode 4 of the Backup Podcast. Our guest in this episode is a brilliant researcher and a great friend. He started his journey at American University of Beirut and continued at the University of Toronto, where he got his PhD degree. His research revolved around hardware and hardware verification, with his thesis title Power Grid Verification. Currently, he works at Intel, managing his own team of engineers and researchers, focusing on systems on chip design. He is Mohammad Fawaz. Mohammad, welcome to the show.
Hello. Thank you so much. Thank you for having me.
This is great. I tried delivering your background, but I have a strange feeling that you might do a better job than myself.
You did. That was perfect.
Could you give us some more information on how you got to the place that you are right now?
Oh yeah, for sure. So yeah, as you said, I did my undergrad back in Lebanon, American University of Beirut. I moved to Toronto in 2011, and I was in grad school for 6 years. I did 2 years master's, 4 years PhD. I was doing more or less the same thing. So that's power grid verification. And I joined Intel in late 2017. So it's been 2.5 years now. So I guess power grid verification is not totally related to what I'm doing now, but it was,
Yeah, give us a hint. What, in layman's terms, what is a power grid verification?
So I guess the way I think
I know that is not easy to explain it in layman's terms, but could you give it a try?
So think about it this way. So every single chip has some parts on it that no one thinks about, which are those little wires that power everything. Right? They don't do anything. They just make sure everything works. They don't do any logic. They have no functionality, right? But you still want to make sure that they work, in the sense that they still deliver the right voltage to every part of the chip. And you have millions of wires, and making sure that they all work as they should, they all deliver the right voltage at every single point in the chip, is a hard problem because of the large number of nodes on the chip. It's a very similar problem to what there's a power grid verification problem in a city, let's say, on a normal high voltage power grid, where you can think of every house as its own logic element, if you will, right? And then you have this large grid that powers this house and that big commercial building, and then the street light and so on. And you want to make sure that every single house gets the 110 volts, right? More or less. If that goes down to 60, right, my power is going to go down. I'm not going to get the light that I'm getting now. So that is the problem that I worked on, of course, on a much smaller scale, on the chip itself. So as I said, the reason why that problem is hard is because you have basically billions of nodes today on a single chip, where you have to make sure the voltage at every single point is what the spec says it should be.
For the chip to work properly, and every component of it outputting the right numbers, let's say.
Yeah, basically your gates would stop working if you don't give them the right voltage, right? The same way that my light here would go down if my power is 60 volts instead of 110.
Which is a great analogy. That's I didn't know that we're gonna go to such a good start here with the analogies. But let's keep them going. So you finished your PhD, and then you immediately went to Intel to work as a, systems on chip design researcher. Can you give us like the top three things that uh, surprised you when you switched from in academia or your life going to Intel?
Well, I guess the biggest thing with industry, which, you know, I was in academia for, or at least a researcher for 6 years, and then 4 years before that as an undergrad. So technically 10 years in a university setting where, um, you're protected by too many things, right? This is by no means an attack on academics, but you know, there's a protection there. Your supervisor is doing, is deciding what the problems are going to be. Um, you go to industry, and the stakes usually are higher.
Mm-hmm.
There's a lot more money on the table. That's, to be fair, and every little decision affects a large corporation, right?
Mm-hmm.
Um, so,
And
you know,
yourself too.
of course. Um, I guess the seriousness of things in industry is a distinguishing factor. I feel. In academia, you get to do. I feel things are a little more lenient, and how can I say this? Not to say that reviewers and conferences are lenient; they're not. Um, but you get to do things outside the box. You get to explore things that most likely will not ever be used, and that's perfectly fine, right?
Yeah.
And that's what academia is. It's I try things. I just go out of the box and I throw things at the wall and see what sticks. Some things might stick, some things might not. Most things will not, and that's perfectly fine. That's what this academia is all about. It's part of it is cheap labor, which is the sad reality, and um, you get to try things, and if they don't work, you showed that they don't work, and you publish that. Right? That's very that has no place in industry. If it doesn't work, you shut it down the first day and you move on to something else. Uh, no one has time for this crap, basically. um,
that
that's
that is so true, and the feeling of the importance of the impact of every decision that you're having, and the sense of the responsibility of that decision. That's what you're saying. That was the biggest difference between your bubbly world in academia and the real world and the real stakes in Intel. Is that correct?
100%, 100%. The other thing, I guess, that might be more of a personal thing, the quality of the code is just a whole other level, right? That might apply to everyone, I guess. I don't know, but in like the quality and the seriousness of the code, and it just things have to work. You have to consider all the corner cases. There's no You're not allowed to slack, right? And if you're trying to publish a paper, you just try to make things work. No one's going to look at the code ever again. That is not the case in industry. And you write the code so that someone else looks at it potentially 20 years from now, and you have to keep that in mind. And that's why I keep saying, like,
Mhm.
the stakes are just higher.
Great. And the stakes are high, and especially on the systems on chip design that you started, that's you're focusing on. Can,
Hmm.
can can you even tell us like what is a system on chip?
So,
Because most people
sorry.
are kind of like getting afraid from all these acronyms and this tech lingo that
So
we're
to be
using.
fair, when I first joined, I guess, a weird story. That
We
was my
love weird
title.
stories here.
As SOC design engineer, and there were very weird reasons why they gave us that title. But that's not what I do more specifically.
Mm-hmm.
In fact, that title changed recently to FPGA software engineer,
Right.
which is a lot more descriptive of what we do. Um, so what I actually do is, develop software for FPGAs,
Hmm.
and that's a more descriptive title. Um, to go into this a little deeper,
Hmm.
the FPGA is just another piece of hardware, just like the GPU, the CPU. You have FPGAs, which serve a very specific and potentially different purpose than other pieces of hardware. They have their own characteristics, and the most important one is the reconfigurability, which means you can reprogram the FPGA to have any logic on it, unlike the
Hmm.
GPU and the CPU. Um, you can literally just strip down all the wires and build it again, just connect the wires inside it in a totally different way and get a totally different system to do whatever you want. Um, so that's what an FPGA is.
Can you give us an
And
example of why do you want to do that? Like
so
how FPGAs are being used.
so on the extreme end of things, you have ASIC, and I'll get to why I'm talking about this in a second. ASIC is basically, you know, um, let's say I'm a bank.
Hmm.
I need to train certain models for certain machine learning models, and I need to do that in a very specific way. So I hire some hardware engineers, and they design my machine learning chip using RTL or some low level language that describes what the logic looks like.
Hmm.
I'm not writing software here. I'm just literally plopping up, I'm describing a circuit that does a specific thing, which is to train a particular model. And the reason why I want to do that is because this is virtually the fastest way to train the model versus doing it on a CPU or a GPU. Anytime you have a piece of hardware that is specifically designed for your own needs, chances are you're going to get the highest performance out of that chip.
Hmm.
You can design it in any way you want. Um, Now, the problem with this process is even though you're getting the high performance, you're getting the right amount of power that you want, uh, the price you pay is a long time to build the chip. So you're waiting potentially a year or two for this to be fully designed and fabricated and brought back to you. And you're paying a lot of money.
Hmm.
That's a very expensive process. On the other end, you have the CPU, which is the most versatile chip, which, you have a CPU on every computer. It does anything you want. Like any program you can think of, any application you want to design, you can just do it on a CPU.
Hmm.
Maybe in not the most efficient way, uh, but you can do anything on a CPU. In the middle, you have the FPGA and a GPU. The GPU being the chip that is, it has its own instruction set, it's fixed logic, um, but it has a lot more cores than a CPU, and you can do so many things in parallel on it, and that's its main characteristic. The FPGA, on the other hand, is uh, is a piece of hardware that allows you to do what the ASIC does, right? You're basically saying, I'm gonna take that RTL, the design that I was going to send to the fab, to the fabricators,
Hmm.
and plop it on the FPGA and do that in a much faster way because programming an FPGA is much faster than a year or two. It takes a few hours, and now you have your design on the FPGA ready to be used. So that is the main advantage of reconfigurability. Um,
So it's like a Lego set that you're changing
pretty much, pretty much,
the
pretty much.
configuration, and then you from so since CPU works everywhere, right? It can do anything, So, and you're saying FPGA is something between an ASIC, which is again a chip, but does one thing. It might do changing the channels on my TV. Or there is one chip over there. I don't know. Probably it's an ASIC,
Yeah,
right?
exactly,
That
exactly.
changes the channels on my TV, and the CPU that can do everything.
Hmm.
And in between these are the FPGA, which is a chip again, but it changes its structure. So that CPU has software, where FPGA has hardware.
Basically, so the way the CPU works
Mhm.
is the logic itself is fixed, right?
Okay.
But you have what we call an instruction set, which means it's you have your CPU logic glued there. It's fixed, and now you run things through it to do specific things. And uh, you say I want to add x plus y, and then that comes out as an instruction, and then they go to the little piece of hardware that adds two numbers, and then you get the data back, and then you store it to memory, and you pick up another instruction, and you keep doing that, and that's how the CPU works. It's just what we call a pipeline. uh, the FPGA doesn't have an instruction set, right? You're literally describing what the hardware looks like, versus you know you can build a CPU on the FPGA if you want, right? In
Okay.
fact, that's something some people do, is to prototype certain small CPUs. You could just take that logic and plop it on the FPGA. Now you have a CPU on your FPGA. Um, so that is what I mean, is you can build anything you want, and you
Mhm.
can run through it anything you want. So you could build that adder there and have your input being taken from the outside world versus being taken from the instruction. You could do anything you want. That's the beauty of it. Just like you call it, it's a Lego set. Um, you have all these blocks plopped in there, and you can connect them any way you want.
Hmm. And well, most people know what a CPU is. I don't know if probably they can picture one,
Hmm.
uh, or they have seen one, and they know there is one in their computer. Maybe they
Yep.
know that some people that the GPU exists, a graphics
Hmm.
processing unit, which is usually used for video and for graphics processing, as the name implies.
Hmm.
Uh, but I don't think most people have heard of an FPGA. Why do you think that we haven't seen like a major adoption of the FPGA architecture?
So that is a very good question. Um, First of all, you don't have an FPGA on your computer. Most likely, your personal computer does not have an FPGA on it. Uh, it you know, for most people, it doesn't serve the purpose that you want, which is I want to open my browser and watch YouTube, and right?
Yeah, what's cats and
Unless
dogs?
whatever it is, um, you probably don't need an FPGA. Just like you probably don't need the highest performance GPU. Most people don't need that, unless you're a hardcore gamer or you're mining Bitcoin. You're not going to need the big GPU clusters, right? Um, FPGAs are, again, as you said, are less popular than CPUs and GPUs. Um, and the main reason for that is that when you buy an FPGA as a user, I can't plop it and use it unless I know what I'm doing. It's a difficult piece of hardware to understand and to program, right?
Mhm.
You buy a GPU, you plug it in, you run your software on it. You can use CUDA if you want, and you write software, and then you're good to go. If you want to do some computation on your GPU, like mining Bitcoin, or you just plop it in your computer and use it as a graphics unit to play video games. Um, an FPGA, on the other hand, when you buy the FPGA, it has nothing on it, meaning it doesn't do anything. It has all the Lego pieces on it, but it doesn't do anything, right?
It's not
Someone
assembled.
has to commit. That's pretty much it. It's like an IKEA box, right? You get to read the instruction manual, and someone have to sit down, has to sit down and you know write RTL, which is painful. And
Sorry, what is RTL? Because you said it before, and I
right,
don't think most people are familiar with the term.
RTL is can mean different things, but for the FPGA it means Verilog, which is a specific language, an HDL language, a hardware descriptive language. So it's basically a language that allows you to describe what a circuit looks like. It just says, connect this wire to that wire and now put a gate here and connect this to that. That's what it does, right? It is not, uh, it has, you can think of it as a high level language like C++
Hmm.
or Java or, those languages that most people have heard of. Verilog is more the word descriptive is there because you're describing the circuit. You're not more than its functionality, but more of how it looks like.
Hmm. Hmm.
Right?
So it's like the instruction kit
Pretty
on
much.
that IKEA thing.
Exactly. You open the first page and you have to connect this to that. Yeah, pretty much. Um, Now, if you've ever assembled IKEA furniture, you can, you know, it can be painful.
Hmm.
And if you miss a screw, uh, you know,
You have to buy
you
it
know,
again.
you know, you know, so with FPGAs, writing RTL is painful because imagine having to do that for a large design. You have to figure out, or you have to decide where every gate goes, and uh, there are some things that help you along the way, but in general, it's a painful process, and it can take months and sometimes up to a year to finish one design that is optimized and does what you want it to do. So it's a difficult process, and that's the that's the first reason why FPGAs have not had the traction that CPUs and GPUs had, because they're harder to use.
Oh, and so since you from the context of what you're saying, I believe FPGAs are more used in like rapid prototyping. Want something or testing of a certain system. But when you say that it takes a long time to implement and code that in RTL, in that time, can I just go straight to the ASIC and work there and just skip the FPGA project
So
altogether?
you could, but that design time you still have to do anyways. Like that time where you have to sit down and write the Verilog or the RTL or the description of what the logic looks like, you will have to do that anyways,
Oh, okay.
right? So the question is, do you want to send that to Fab and make the chip and pay all that money, or do you want to send it to, or do you want to just compile it on the FPGA within hours and get the result?
Oh, okay.
On an
And
FPGA, you can do that. You know, you
any
make a
number of
design, you
times,
test
yeah.
it out, and you can test that every day if you want. And it's like writing software. You can keep testing it along the way until you get to the performance you want.
Hmm.
Uh, so that is the advantage over ASIC. Um,
Are there
Now you
any
may,
other differences, like in performance or in power consumption?
so again with ASIC, anything goes. It's you know, uh, you can do anything you want. They're obviously more flexible than FPGAs. FPGAs, even though they're flexible, they still have certain constraints. You're still constrained by how many blocks you have, how many RAM blocks you have, how many DSP blocks you have, how many registers and how many flip flops, and all these logic things. They're there, and you're constrained by where they are, and you're constrained by the periphery of the FPGA. While in ASIC, you can do anything you want, right?
Hmm.
You can build the chip that looks like a little trapezoid, and you can anything you want. Like no one's stopping you. So obviously, there's most flexibility there. Uh, so that I guess that is the main difference. Now, FPGAs have been known for their low power for what they are and what they deliver,
Mhm.
versus something like a GPU or a CPU. Um, and the reason for that is when you run something on the GPU, you're basically saying you're basically operating the whole chip. The whole chip is running. When you run something on an FPGA, you're only using the parts, or the only the parts that are being used are drawing power, right?
Mhm.
Everything else is shut down. So on average, an FPGA will consume less power than a GPU for the same application. That is one of the attraction points versus something that you run on a GPU. As I said, the long development time and the lack of usability for FPGAs have been a problem. And this is where I come in. I guess this is the punchline.
Mhm.
Um, the There's been a recent, I guess, wave in the past 10, 20 years, um, what's called high level synthesis, which is a whole area of research. And, we have a product for that, which is basically allowing developers to write high level source code in C++ or OpenCL, which is another C-based language, to compile for an FPGA. So you write I write my C code or C++ code, which is very easy to do. It's the same process as a CPU development. It's developed for a CPU, and I take that code and I compile it for the FPGA, and I'm done within a few days, right? If I want to iterate a few times, versus a 6 month wait period. So that is high level synthesis, and that's what we do in my team. We're basically saying, let's take that high level code and do some transformations on it. You want to parse it and then optimize it and then transform it into Verilog. That's the RTL I was talking about.
Mhm.
And that process takes minutes. And now I compile that Verilog, and now I have my Verilog. I have my design. I'm done, right? And that transformation has been worked on by many people. There's a big area of research there. We have tools for that. We have compilers for FPG, for OpenCL. Um, we have a new product called oneAPI, which is, I could talk about uh, in a second. But the point is, the usability problems of the traditional usability problems of an FPGA are being addressed that way, uh, by allowing people to program the FPGA from afar. You're writing high level source code, which is easy to do. Someone in their first year of engineering school, they learn C++, and they can now program the FPGA. You don't need an expert RTL designer who has to spend 6 months to get to the final design.
So basically, you're taking the IKEA instructions that is in Swedish and in 100 pages, and you
Mm-hmm.
turn it into a two-pager presentation in English.
That's a good way of putting it. Yeah, I would say so. Yeah.
I can imagine that for sure. I can see the value in rapid prototyping there, and especially since it is RTL, as you say, it can be both used as ASIC design as and is an FPGA, correct?
Mm-hmm.
So basically, it's not just FPGA, it's just design in general, which is
Correct.
immense. Um, do you see like I, probably there is some information loss since you're going that high level and
Mm-hmm.
everybody can do it, like how and I'm pretty sure that that is perfect. That is not perfect. Can you talk about what is going on between this level that you're talking about, the C++ level, and the Verilog level? How we can condense it down, and what information is being lost, and what are the difficulties of this process?
So the biggest loss usually is performance, which um, you know, going through that translation and getting the same performance as the 6 month RTL developer sitting down and coming up with a final fine-tuned design to the single register, getting to that performance is difficult.
Mhm.
In some applications you could do that, uh, but it is difficult, and there are still limitations in most compilers. um, and by compiler I mean that transformation is called, or that piece of software that does the transformation is the compiler. um, there are certain differences between there's a lot of difference between the C++ level and the RTL level, and being able to describe everything in that high level language, and assuming you're going to get what you want uh, in the RTL, you know, it's a difficult process. There's a lot of roadblocks, both in the compiler land and with whoever is trying to program. Um, so even though we say, yes, someone can sit down and write a C++ code and they're done, and now you have your final design, the reality is not usually the case. The reality is you go through the process, that same process, over a few weeks and sometimes over a few months. Uh, but it's a less painful process than writing RTL. I guess that is the key point. Um, in many applications, people are willing to lose that 10% performance, let's say. I don't know what the number is, it's application dependent, but they're willing to lose that performance number for a several X boost in productivity. That is a very key point.
But FPGAs are, as you mentioned before, are used in this notion of high performance computing.
Yep.
Can you tell us what is high performance computing, and what is what's different between that and my computer that I have here, which I consider is very high performance like. And what's the role of an FPGA, or to that high level language that you're developing? What's the role of that high level design that you're doing right now?
So I guess the high performance computing land, um, the keyword there usually is parallel, right? I
Hmm.
need to do things in parallel. Whether you're talking about a multi-core CPU or a GPU or an FPGA or ASIC, whatever it is, you want to be doing things in parallel. Um, and the easiest way to think about this is, if I need to add 100 numbers on a traditional CPU, ignoring all the vectorization and weird things that we could do today, um, to add them, you need 100 steps, or what we call them cycles. You add two numbers at a time, and you get 100 numbers out one step at a time. Like, it's a slow process. A GPU is able to do that in one shot because you have too many different little computational blocks, and that allows you to parallelize anything you want to do. So if you're adding 100 numbers, or if you're adding, um, you know, you could do that in a parallel way. Every block can take two numbers and they add them and so on. And you keep doing that. And now you potentially can do that in one cycle. If, let's say, you're adding 100 numbers, but another 100 numbers. Um, you could do the same on an FPGA because you could build whatever hardware you want to do that. Um, And if you were to take a high-level language like C++ and write a code to do that and compile it for the FPGA, the FPGA or the compiler will build logic to do this as fast as possible, right? So the way the parallelism works on an FPGA is what we call spatial parallelism. So you could potentially, you know, build 100 adders and now you're good. You just plop them on the FPGA and now you get your 100 numbers out in one shot. Um, so that is the key point in high performance computing is I want to do as many things in parallel as possible.
So what's the difference between a high performance CPU, for example, and my CPU here, or everybody's CPU in their laptops?
So, I mean, not much really. It's about how many cores you have. I guess a high performance CPU is just a CPU that is fast and has too many cores and probably lives on a big farm with many other CPUs. And that's a big CPU farm, right?
Also,
But
you.
high performance,
Oh,
yeah, you're just plopping hardware all over the place and trying to do things in parallel as much as you can.
mm-hmm.
The CPU itself is not exactly special, right?
Mm-hmm.
You could buy the latest Intel CPU, and that is considered high performance today, and you could plop that with 1,000 other CPUs of the same style, and now you can do too many things in parallel at a time, and that's the key point with high performance computing. Now you can do that, or you can go for the GPU if you're trying to do small tasks uh, that needed to be done too many times, or the same goes for an FPGA. Um, so, deciding where to go is another question. But this is what we're seeing today. Like, the Amazon AWS cloud, the Microsoft Azure cloud. They all have all these farms of actually GPUs, CPUs, and FPGAs, and they allow vendors to go there and use whatever they want to accelerate any piece of hardware you have. Um,
How they're
so,
using the FPGAs?
so the FPGAs are there for you to use in any way you want, right? Just like a
Oh,
GPU.
okay, okay. But you have to program it even in the AWS.
Yeah, of course.
Okay.
So you take on a portion of those FPGAs. You say I'm going to be using those. You program them, and then you can use them,
Mm-hmm.
accelerate whatever you want. Um, as opposed to having to buy the FPGAs yourself,
Mm-hmm.
which is another option if you like, but they're there. In fact, Microsoft is using their FPGAs for that, but they're also using them for network acceleration. That's another big application today, where your FPGAs sit uh, and act like what's called a smart NIC. It's a piece of hardware that sits by the servers and processes the large requests that come in, right? So traditionally, you do those in software, uh, but the new wave of networking, I guess, is trying to do those on hardware because you could do them much faster. And by that I mean a request comes in, someone needs to access the cloud, something needs to process that request. Like you have all the networking layers, and it's a difficult problem. But doing it on hardware, it turns out that the FPGA is an excellent uh, piece of hardware to do that.
Mm. So more on the high level synthesis right now. Uh, uh, does it affect high performance? Does it enable high performance computing? Is it gonna change in the future?
So that is the hope, right? That is what we're working on. Um, Again, a lot of people are already adopting that over uh, other accelerators, other ASIC or GPUs. It is there, and a big reason why people are excuse me why people are adopting that is high level synthesis, right? Um, People want the flexibility, people want the usability, people want to be able to sit down and write C++ code and be able to get the fast performance um, much quicker than having to sit down for 6 months and write RTL, which could be a painful process. Uh, so, yes, um, I guess HLS or high level synthesis is moving people in that direction. There's a lot of adopters of that new um, paradigm, if you will.
Uh, in my opinion, hardware is the game changer that turned the tide towards the this new AI wave that we're seeing right
Hmm.
now. Um, Hardware empowered us to become smarter, to become enabled us to have the capabilities that we have right now.
Certainly.
So most people maybe are not aware that almost most of the algorithms, the machine learning algorithms and the AI algorithms that they are out there, they were discovered decades ago. The
Hmm.
original concept of it, but since at that point hardware was not there, we were not able to process that much information, and
Yeah.
we were not leveraging uh, those algorithms for so many years. And right now hardware has enabled that and powered this AI revolution that we're seeing right now. How is high level synthesis how do you imagine high level synthesis impacting other technologies or other ecosystems into the future? How high level synthesis is gonna change the tech world as we see the hardware world, and by effect the downstream applications of it.
Okay. I think the key point with high level synthesis, and as I've been saying, it's the usability, right? Um, the key point here is you want to be able to write software and accelerate it on any of the possible chips you can target today. Um, and that gets us to the point of heterogeneous computing, I guess. The uh, AI wave, any piece of software you have that, any AI algorithm, machine learning, it all has so many pieces in it that, and different pieces work best on different hardwares, most likely. I guess. So what I'm not an expert in AI, but I suspect a lot of that math works best. Some of that math works best on a CPU. Some of it works best on a GPU. Some of it works best on an FPGA. It is not easy to decide what should go where. But I think the fact that you can now write C++ code from A to Z, like you have this full code, and at different pieces you say, hey, you know what? I think this works perfectly on a GPU. It's just a little loop that is adding all these numbers, and those multi-core GPU can do that very easily. I'm just gonna offload that to the GPU. That's the offloading model, right? And then I'm moving on, and I'm like, oh, that's a nice piece of software that looks like it works best for an FPGA. It has this like spatial, parallelism, and I could use the pipeline. There's a lot of. It's not a trivial thing to figure out when things work best on this or that, but with experience you can. And now you say, oh well, okay, I'm going to offload that to the FPGA, and you just do it, right? As part of your algorithm. You don't have to go and hire a hardware engineer who would come in and they're expensive and then sit down for 6 months and do the logic. You're just doing it as part of your piece of software that you already wrote. And then you move on, and then you're like, oh, well, the rest of the code works on the CPU. I'm not going to bother. and now you run it, and that's it. And now you're making use of all the pieces of hardware that you have access to, whether it's your own farm or AWS or whatever it is. Um, and high level synthesis enables that, right? Without high level synthesis, you can't do that. And that is the model we're trying to go for with oneAPI is um, allow people from a single source or multiple sources to target different pieces of hardware and in a very usable way. And you can experiment with things, right? And that's the key point here is I could repeat that process with any piece of software if I have. It's a very quick turnaround. My feedback loop is very fast. I could say, oh, well, you know what? I think I don't want that here. I'm going to move it out. I think I want this part not to run the FPGA anymore, or maybe I want to pull more things in. And I click compile, and now I have my design, and I run it again, and I see my performance. Maybe it's better. Like the experimentation part is much faster
Mhm.
versus um, writing RTL. So
And I guess like even if the performance is it has degraded like 10% from an ASIC, if you're showing that one system is better than the other, again it's scaled for that 10%. So when you're trying to implement it, it's still gonna be better than the other system, right?
oh yeah, I mean exactly. You just keep running and then see what comes up. Once you're happy, so to be fair, you're not going to be comparing to RTL because you don't have RTL. You're just trying to do your best and see what works for you. And when you get your throughput numbers, your power numbers, and you're happy with the results, you go and move on. Um, the problem with ASIC is, yes, it's difficult. Um, it's a hard process. It's expensive, and if your requirements change, you have to start over, right? If my algorithm changed radically because now it's not suiting my needs anymore, I'm going to have to throw that chip away and start over, which again is very expensive. People don't like that.
Yeah. I definitely can see the value of it, and since I deal with stakeholders all the time,
Mhm.
I can tell you that changes is all that the client does. It's
Exactly.
it's their job to change the specs and change the requirements every other day. So we have to expect
Mm.
that. But you mentioned one API. Can you elaborate what is that a product of Intel's? Can you give us
So,
like the
mhm.
sales pitch of one API?
Yeah, to sound like a salesperson here, but one API is trying to do exactly what I was talking about. Um, so it's a recent product. It was rolled out a few months ago. Basically, what we're trying to do is to develop this ecosystem where you can write your piece of code in potentially one file and offload different pieces of that code to different accelerators. And by the way, one of those accelerators could be an ASIC chip. I haven't seen that done, but someone else could probably comment on that better than I would. But the part I'm working on is the FPGA. So allowing you from that single source and that offloading task that you write, you tell me I want this to go on the FPGA. Uh, my role comes in is and would be to uh, do that transformation in the most efficient way possible, right? So that requires knowing what the best RTL is for that particular application. Doing that transformation, uh, is not trivial. It's in fact there's a lot of compiler theory involved, and compilers are known to be, um, what they say, they will be dragons. Oh, it's probably they say it's the most difficult piece of hardware or piece of software you can write because it's an extremely difficult problem to come up with the best RTL or the best Verilog, or even for CPUs, come up with the best uh, set of instructions or set of CPU instructions that come out of your CPU or C++ code.
Mm-hmm.
Um, so this is where my involvement comes in, is that offloading. Once you do that, I take that device code and I transform it to RTL, and I make sure that happens in the best way possible. Obviously, the team is large. There are multiple people working on this, multiple places, but this is where I guess my team is.
So oneAPI is this grand project of Intel's. They're saying, okay, you have a ton of stuff that you want to process, and you want to offload those jobs or that workload into different parts of a system. Let's say you,
Mm-hmm,
you want to offload a summation into the FPGA. You want
sure.
subtraction to CPU. You want multiplication. You want to the GPU.
Mm-hmm,
And each one of those offloading mechanisms have a compiler with it, a transformation set that does that C++ code into RTL code, as you say, and executes that in the end. And your
mm-hmm.
team is, and you're leading the team that is focusing on the FPGA part of the process.
I mean, I'm part of the management chain of that, so
Okay, okay,
I'm
okay,
not I'm
okay,
not
okay.
leading the team that does all of that, but yeah,
Great, great,
I'm a
great.
subset of that team, I
You're an
guess.
important subset of that part, and which comes up nicely because you mentioned before the term heterogeneous computing,
Mm-hmm,
and I think that's like a very good representation of what a heterogeneous system is.
exactly. Mm-hmm.
Can you give us like the definition of what is heterogeneous computing, what is its pros, what is its cons, and why is interesting at all?
So I guess the biggest advantage of heterogeneous computing is the ability of to take advantage of the different uh, architectures that are available to you. Um, Again, that's not something that was not possible 30 years ago or so. And with I think we've seen that in the last 15 years, GPUs started being used as general purpose computing devices, and then FPGAs started coming along, and high level synthesis came along. And today it's only in recent year where we are now able to uh, offload different pieces of our software to different uh, architectures and take advantage of them. That's what heterogeneous computing is all about. It's just um, making use of different architectures. And the architecture is how a hardware is built. So FPGAs have their own architecture, which is based on flexibility and reconfigurability. While GPU's architecture is the multi-core thing. You have too many cores, too many small cores doing the same thing. A CPU's architecture is the versatility. If CPUs can do whatever you want, and they're best for everyday use. So taking advantage of this big ecosystem is what the heterogeneous is all about. Now, the biggest disadvantage of this is it is still very difficult to use, right? Uh, Even CUDA programming, which is basically a very mature um, paradigm now, it's been around for a while now. Um, it is not easy. You have to keep in mind too many things about the GPU. Even though you are developing a piece of software, you're writing software, right? You think, oh well, I'm writing software. Why do I have to care what the GPU looks like? Wrong. You have to know what you're targeting. Generally speaking, software developers, or at least most software developers, do not need to care about the architecture of the hardware. You just write your code, you compile it, you're good to go. You think the compiler will do the right thing, and you go to sleep. For in heterogeneous computing, that's not possible. um, you need to understand your hardware. And for GPUs and FPGAs, you will probably have to apply what we call attributes and pragmas and things, annotations on the code to say what you want to happen in hardware, right? You write your loop and you say, oh, I want that to look like this on hardware. uh, you don't really care about that on the CPU. You trust the CPU will do the right thing. For GPUs and FPGAs, you need to understand what goes on behind the scene. And then I guess that's the fallacy with HLS being this, it's high level. I'm going to write C++ code and throw it out, and I'll go to sleep, and I know I'm going to have the best performance possible the next day. The reality is, it turns out it is not the case. In most cases, you need to hire software engineers who understand some of the hardware, who know what goes on behind the scenes, more or less. They don't need to be expert Verilog writers, because they're not going to write Verilog, but they need to understand the architecture of the FPGA. They need to understand the architecture of the GPU. They need to understand that memory transfer is a bottleneck. It's not easy. Like transferring data from the CPU to the FPGA or to the GPU, doing things and getting the data back. We're talking gigabytes of data. It is not easy. You have to account for all of that. So I would say the biggest disadvantage remains the usability and the difficulty of it, even
Interesting.
with high level synthesis. We've come a long way with FPGAs, at least, from writing raw RTL, um, but we still have a long way to go, and we're not even sure that's possible for someone to just write code and forget about it. Like
Uh,
out of the what we call out of the box code, for it to work at the top performance you want, is not entirely possible.
yeah, that sounds amazing. So, Mohammed, we talked about FPGAs, we talked about high level synthesis, we talked about heterogeneous computing, one API. Can you give us like a small 10-word summary, if you can, of what we're talking about and what's going on in the future?
All right, so if listeners want to take one thing out of all of this, is knowing that, I guess they know that CPUs and GPUs exist, know that FPGAs and ASIC exists, and now you have these four different architectures that are out there, and they excel at different things. And the future potentially could be, you have on your laptop all three kinds of architectures, or all four kinds of architectures, and you know software engineers will be able to write pieces of code that could target either of those, or more, one or more of these architectures, um, which contradicts the old model that we had for 20 years or more ago, which write software and target the CPU and you're good to go. The heterogeneous computing model will open the door to many uh, real world applications, um, especially with the amount of data that's flowing every day, more and more every day. So we'll see how it will play. Yeah, I mean, hardware is what makes things work, makes things work. Um, writing software is fun, but keeping that hardware in the back of your mind is always a interesting challenge.
You have only things to gain from doing that. I can tell you from my experience.
Hmm.
Thank you, Mohammed. Uh, Please, people, go follow Mohammed on his social media. I'm gonna have it on the description below. Uh, if anybody has the same passion, if anybody wants to try the one API, go
Hmm.
ahead. Uh, it's still in beta, but I'm sure it's gonna come out of beta anytime soon. And hit up Mohammed if you're interested in hardware, if you're passionate in hardware, and see what Intel has to offer. Mohammed, thanks a lot for helping me
Sure.
backing up a conscience, and hopefully to see you soon.
No, thank you so much. It's been a pleasure. It's been a lot of fun.
This is it. Your mind is now backed up. To learn more about the topics discussed or the guests, follow the links in the description. Now you have the chance to subscribe, rate, like, dislike, and review the show. Also, looking forward to hearing your thoughts in the comments. Awesome. Thank you so much for joining me, and see you next time.